Okay, hello everyone and welcome back to your YouTube channel and welcome to this fantastic video today. As you must be aware, I am working in this series of videos related to fundamental concepts, basic concept of power engineering. And a very important aspect that we need to be aware is there is a device that is called power transformer. And these power transformers, they are extremely useful when we are working inside power systems. Power transformer, as I say in one of my previous videos, it was the device that allows us to establish a successful transmission system at the very early stages of the power utilities. So the transformer has been a very, very important device for the power system operation. So today I have a very simple, a very important, very interesting numerical example related to the ideal transformer. So today we are working with the two-winding power transformer, and in this case today we are working with the ideal transformer, and specifically we are considering the transformer working inside a very small power system that is working in a steady AC conditions. And the plan today is that we are calculating some very important indicators like the active power, the reactive power, the efficiency, and regulation. So without further delay, let's start by reading the statement of this very exciting problem today. As you can see over here, the statement is telling you the figure Q1 here below show a two-winding ideal transformer. So you must be aware this is an ideal transformer, the very simple one. There are not internal losses in this transformer, so the internal components of this transformer they are not included. So this ideal transformer is connected to a load using a switch SW. So if we go here down, you can see the figure Q1. And this is the circuit model representing a voltage source here on the left-hand side, 240 volts. And there is a resistor connected to the primary of this very exciting ideal transformer. But what is extremely important is that we have this switch that is connecting a load to the secondary winding of this ideal transformer. So here in the circuit model on the right hand side, you can see that we have a load, and that very specific load is modeled by a constant impedance, and you can see the numerical values over here. The resistor is 1 ohm and the inductive reactance is 1.75 ohms. So let's keep reading here this statement. The transformer has connected a resistor R1 on the primary side. You can see here the resistor, and the numerical value is 5 ohms, and a load on the secondary side, and you can see over here the numerical value. The approximate equivalent circuit is depicted here in the figure Q1, this very important figure over here, and the transformer ratio, and you must remember the transformer ratio is defined in terms of the number of turns, and here the numerical value of the transformer ratio is 5.0. So as you can see, we have two cases over here, a case where we have the switch open, and then a case when we have the switch closed. So when the switch is open, we want to calculate the currents, primary and secondary, in a complex form, in a polar representation, the magnitude and the angle. But also we want to calculate those voltages over here. You can see this is the terminal voltage here at the terminals of this ideal transformer, and also the secondary voltage over there. So again, we are calculating the complex number, the phasors, and in this case, we are considering a polar representation, and that means that we are interested on the magnitude and the phase angle. Then the switch is closed, and again, we are interested on primary and secondary currents, those voltages that we already defined, but also we want to calculate the active power in watts and the reactive power. Also, we want to calculate the voltage change expressed in percentage to the open circuit. We will later see that this is what we call the voltage regulation. And finally here, we want to calculate the efficiency, of course, in percentage of this system, okay? So let's start the solution. What is important that we need to understand here, what is extremely important is, first, let's consider the condition when the switch is open. So I believe everyone here watching this video, they can see that if this switch is open, so this constant load here, this impedance load over here is fully disconnected, from the secondary winding of the transformer. So it's clear that this is an open circuit over here, so the secondary current is 0. So again, this is an open circuit, and as a consequence, the current here is 0. So what we need to consider is that an ideal transformer follows the very well-known transformer ratio. So if we know that the primary current is 0, we can calculate the secondary current, because using the transformer ratio, we can extract over there the value of the primary current in terms of the secondary current. And you can see here in this equation, I2 is the secondary current, primary current is I1. What is important over here is that we need to divide by 5 in order to obtain here the primary current. The situation over here is that the current I2 is equal to 0. So as the current I2 is 0, the primary current, when we multiply by the transformer ratio, well, what you can see over here, if the secondary current is 0, well, in this ideal transformer, the primary current should be 0. So it's very, very simple. Secondary circuit is an open circuit, so the secondary current is 0. And then when we apply the transformer ratio multiplying the secondary current, that is 0, that means that the primary current is also 0. The next step is we want to obtain this voltage over here at the primary side of the ideal transformer, and also we want to obtain the secondary voltage here at the transformer. So what we need to do is the following. If the switch is open, this current here is 0, but also the current here is 0 at the primary side. So I believe every one of my students can see that we can apply here the Kirchhoff voltage law. So if we apply Kirchhoff voltage law, Kirchhoff voltage law will tell you that the voltage, the supply voltage V1, should be equal to the voltage across the resistor plus the voltage across the primary side of the transformer. And this is this beautiful equation over here. However, what is important is that you remember that if the switch is open, the primary current is I1 is 0. So this term over here, multiplying the resistance R1, that is a numerical value of 5 ohm by 0, that will give me a 0 voltage drop. So at the very end, you can see that if the switch is open, so the voltage V21 is equal to the voltage 1. And from there, it's very simple to everyone to see that the primary voltage of this transformer will be numerical equal to the supply voltage. But that is because the switch is open. So now we know here this voltage. We know the voltage on the primary side of this ideal transformer. To obtain the voltage on the secondary side, what we need to do is just using the transformer ratio. So using the transformer ratio, we can see over here that dividing by 5, because this is a step-down transformer, we obtain that the secondary voltage is 48 volts. So what I am telling you is that if the switch is open, so as you can see over there, the primary voltage will be 240, 0 degree angle, and the secondary voltage will be 48 at 0 degrees. So the next step, and very important step, is the condition when we close the switch. So when we close the switch, the condition change. Because now, when we close the switch over here, it will be a current over here if the switch is closed. So we will have clearly a closed loop here at the secondary. So we will have a clear primary current moving here on the primary side. So the best way, the most simple way to solve this problem is basically, well, let's refer this impedance from the secondary side of the transformer into the primary side. In other words, what I am telling you is that we can refer this impedance from the secondary to the primary. And that is the easy way to solve this problem. And every one of my students, they must remember that we have a very amazing equation, and that very amazing equation will let you to refer the impedance from the secondary side to the primary side. So if you look this equation over here, this will be the impedance referred from the secondary to the primary. So the transformer ratio is 5. So remember that we need to use the square value of the transformer ratio. We multiply the impedance 1 plus 175J ohms by 25, and we obtain here this amazing and this beautiful refer impedance over here. You must remember this is the impedance refer to the primary side. So now you can see that this circuit is extremely simple, because right now we have two impedance in series connection. So we have this resistor 5 ohms in series with the apparent impedance referred to the primary side. So you can see that the equivalent impedance will be 5 ohm plus this impedance over here. And from there, we can calculate the primary current, and the primary current will be extremely simple to calculate by using the Ohm's law. So Ohm's law say that dividing the primary voltage the supply voltage over here, 240 volts, 0 degree, divide by the total impedance, equivalent impedance in the primary side, 30 plus 43.75J. Well, we obtain this amazing current over here, and this is the primary this is the current at the primary side. So as you can see, in the primary side, there are around 4.5 amps moving on this primary side. So the next step is to calculate the current in the secondary winding, and to do that, we are using the transformer ratio. So as you can see, we are multiplying this current by the transformer ratio, and in this case, we obtain the magic number over here that the secondary current is equal to 22.6 amps. Yes, the secondary current is larger than the primary because all my students can see that the secondary current is coming from a step-down transformer. So now we know the primary current and the secondary current, and the next step over here is very simple, because now what we need to do is basically calculating the voltage across the primary side of the transformer. So to do that, what we need to do is use here the equivalent circuit that I showed you with the impedance referred to the primary. So this voltage over here can be obtained using basically the Ohm's law. So using the Ohm's law here, multiplying the impedance referred to the primary and multiplying the primary current, I can obtain over here, and this will be the voltage on the primary side of the transformer. So that is the primary voltage, and the secondary voltage again can be obtained by using just the equivalent circuit, because we already know the secondary current, and this voltage over here is the same voltage V2, and this voltage V2 will be the load impedance multiplied by the current I2. So with that in mind, what we need to do is to numerically substitute in the Ohm's law. So as you can see over here, the voltage on the secondary side is 45.5 volts, and the voltage on the primary side of the ideal transformer is numerically equal to 227.9 volts. So now the next step, a very interesting step, is calculating the apparent power on the primary side. And you must remember that this is a complex number that is obtained by multiplying the voltage phasor on the primary by the conjugate of the primary current. Remember, this small asterisk over here is a mathematical operator that is called the complex conjugate. So the complex conjugate is applied. We know the primary voltage 240, the supply voltage, sorry, and this is the current at the secondary, and we are applying the complex conjugate. So it's a good idea that you refresh your concepts on complex number, but basically we are changing the sign of this angle over here because this is after applying the complex conjugate. So running the mathematical calculations over here, we can obtain the total apparent power, and there are two components when we are using the rectangular form, and this is the active power, 640 watts, and this is the reactive power, 895 volt ampere reactive. So the next question is what we call the voltage regulation. So everyone in my classroom must remember the definition of voltage regulation. So the voltage regulation, as you can see over here, is basically a difference divided by a number over here. This is the open circuit voltage, this is the full load voltage divided by the open circuit voltage. So in the previous calculations, we obtained that the open circuit voltage was 48 volts. You must remember that. And in a full load condition, the voltage drop up to 45 volts. So dividing by 48, we obtain here the answer for the question E. And this is the voltage regulation. This is the voltage regulation 5.011% referred to the open circuit voltage. However, something that is quite interesting is to show to my students that there is a possibility to refer the voltage regulation also in terms of the full load voltage. So we can do that by changing the denominator in the equation. So instead of using the open circuit voltage, we are using the full load voltage, and in this case is 45 volts, 45.5 volts. So as you can see now, the numerical value of the voltage regulation change, and in this case is 5.27. But what is very, very important is that my students understand the difference. In this case, the voltage regulation is defined in terms of the full low voltage, and in this case, the voltage regulation is defined in terms of the open circuit voltage, okay? So finally, we need to calculate the efficiency, and to be honest, this is very nice calculation. You must remember the concept of efficiency, and efficiency is the ratio or the relationship between the input power and the output power. So to calculate this, you must remember that the input power and the output power, they are calculated very simple, because when the switch is closed, the current moving on the secondary is I2. So I can apply over here the secondary current multiplied by the load resistor, and we obtain over here, this is the load current, the output power, 511.7 watts. And the input power can be calculated, and we already obtained this because we already know that the input power is 614. However, if you want to redo the mathematical calculations, you can use this equation: input voltage magnitude, input current magnitude multiplied by the power factor. So we know that the input power is a bit larger, is 614. So calculating the efficiency is simple. Input power 511, input power 614, output power 511. When we put the number together, you can see that the efficiency of this system is relative low, is only 83.3%. And that is because we have power losses between the primary and the secondary, and those power losses, they are created here in this resistor R1 of 5 ohms. So here in this video today, we deal with the concept of the ideal transformer, And in this problem specifically, we have used this switch in order to obtain the numerical values of the electrical variable for two exciting conditions when the switch is open and when the switch is closed. Also, in this video, you learn about the concept of voltage regulation, and as I said before, depending on the denominator of the equation, you can express the voltage regulation in terms of the open circuit voltage or the full load condition. And finally, we also calculate the efficiency of this system, and because there are some losses here, almost more than 100 watts here in this resistor, so the efficiency of this system decrease a bit far from the ideal condition of 100%. So we are reaching the end of this video. So I hope that you enjoyed the explanation, that you understand the concepts, that you follow all the concepts explained here. And if it's like that, please, I highly suggest that you subscribe to the YouTube channel in order that you can get the most fresh information about the new videos, and also to get access to the very specific and special content for the users. And also, if you like the video, please make a like, and also you can put any question at the comments below. Well, it has been my pleasure to be here with all of you talking about single-phase transformer, power, efficiency, and regulation. And this is the end of this video, but we will not finish the video without the classical and the very well-known bye now.